Ladies and gentlemen, welcome to a slightly technical AI introduction. A presentation I called From Zero to I Have an Idea About It. This presentation was formally given at my organization, Campbell Institute of Intelligent Technologies, in April 2024. And since I got pretty kind and nice feedback to it, I decided to share it for the public. So anyone who wishes to learn technical details, very slight technical details about AI can profit from it. So I understand that our time is valuable. So let's straightly define who this presentation is for. A target group I've chosen for the presentation are people without or with minimal technical knowledge on AI. You may have heard in AI before, probably yes, but maybe you wish to learn more. How does the AI work in the background? What are the technical terms, technical theory behind AI, and what the AI actually is? Because many people talk about it, but coming to some conclusion to precisely define what the AI is nowhere to be found. So we'll take a look on that. So the goal of the presentation is to understand the basic AI concepts and terminology from a friendly technical perspective. We will also discuss the impacts of AI in the current society and the future impacts that AI may have. As a bonus, I prepared a practical code example to show you how does the AI look on a very simple example of a classification problem. So how does this code look? How do we work with AI? And also usage of generative AI models, such as ChatGPT to generate text or even image generation that you can use for your purposes as well. So let's get to it. We will discuss also some history about AI. As I mentioned, some AI basics, plus what is the current state of the AI, and we'll briefly touch what the future of AI may be. More precisely, we will intuitively describe and define terms like artificial intelligence, machine learning, deep learning, and learn to distinguish between them. We'll discuss the AI history in a nutshell. We will learn basic terminology and principles. We will illustrate how a neural network is trained. It's for dummies, so anyone without technical knowledge can understand. You will see later. We will briefly describe modern generative AI, such as large language models and diffusion models, and have some demo, how to work with them. How can you use them in your work or personal matters? So, something about me. My name is Patrick Goldschmidt. Currently, I'm a PhD student at the Brno University of Technology, and I focus on cyber threat detection on computer networks using machine learning and AI. So I wouldn't consider myself to be a researcher on AI, but rather I use newest AI techniques in order to improve the cybersecurity. I have a master degree from the Brno University of Technology from a program Cybersecurity and AI. I've worked as an R&D engineer, and currently I'm a research assistant at the Campbell Institute of Intelligent Technologies in Slovakia. My other interests include anything about money, economy, personal finances, investing, even geopolitics that influence the markets and our beloved capitalism, of course. And I am also keen on self-development, psychology, philosophy, and so on. And I really love any drinks with a great taste, and I'm really prefer tea. So I recommend to try a good tea for anyone to improve your well-being. So let's start with the presentation. First of all, I would like you to think about what the AI is in your perspective. You surely heard of it, but have you ever tried to think what is an AI? What's the first thing that pops up in your mind when someone says artificial intelligence? Are those robots? Are those driverless cars? Are those some computer game that is played by a computer? What is AI in your perspective, or what does the AI do? I'll give you a few seconds. You may even pause the video. So I hope you thought about it well, and let's begin our discussion. So what is this AI then? At the beginning, I mentioned that not many people talk about definitions and descriptions, what the AI actually is. Why? Because no widely accepted definition exists, even amongst researchers and academics. There are several definitions, and they are slightly different. So we will introduce one that I find the most general, that describes the concept, and it can be generalized on many other areas. So let's see. So in order to describe what the AI is, we'll try our best, and we'll play a game in the meantime. So let's play Tic-Tac-Toe. I hope you know the Tic-Tac-Toe. The goal is to have 3 crosses or 3 circles in a row in order to win a game, or in a diagonal. So I'm a gentleman, so I let the AI play first. So the AI puts X, I put some circle, the AI put another X, and so on and so forth. And at this point we see that the AI had won, and and I lost. What happened? The AI played the game. It processed some of my inputs, which were the circles, and it was trying to win, to achieve some goal. In order to make this, it had to think and to decide and to make some outputs, which were the X's. So here is our AI definition. We work with some inputs, we work with some outputs, we have some goal, and we need to decide how do we create an output. But okay, do we consider a tic-tac-toe an AI? Like, it's a game, it's a very simple game. Maybe 20, 15 years ago, the people would say that, yeah, this is AI, it's a computer AI, and it's playing games against us. Nowadays, we find this pretty dummy, pretty easy algorithm. Actually, in background, it looks like this. The AI system is thinking about possible moves it can make. So each X that can be put there creates a new branch. Here are only 3, but there are 9 different places to place an X. So there would be 9 different branches. And then the AI starts to think how we can play with the given X. So we can put our circle there, or in any other positions. And the AI goes so forth, and what it tries to do is to simulate how the game will end. So it processes hundreds or even thousands of different combinations of different outcomes of the game in a second or in several milliseconds, which is impressive because we as humans wouldn't be able to solve this state space search problem. So the AI does this state space search. It can be considered an AI. It was considered as an AI in the past. Nowadays, it's pretty disputed, but still, like, the AI plays a game with some goal and analyzes what can happen in the future. So this was the tic-tac-toe game. But now let's consider a driverless car analogy. I believe that anyone, even the academics who are opposed to calling this tic-tac-toe an AI, would agree that if we have a driverless or autonomous car or vehicle, it can be considered an AI. Because what the car does is this. It needs to get to some destination by processing the inputs. Yeah, here we are. It processes the inputs, so it has sensors, cameras, and so on. it needs to get to the goal safely without an accident and maybe as fast as possible according to our specifications. It needs to think about how to get there and decide. And when it decides, it needs to create some output. So hit the brakes or gas or turn out the car to the sides and so on and so forth. So again, we see that this is the same thing as with the tic-tac-toe. We had the same components of the AI. So let's try to define it. What this AI actually is. AI, or artificial intelligence, we call it a technology that when we have a complex goal, such as getting to destination, we act as a physical or digital dimension. So we turn the wheel or put some X or circle into the game. We perceive the environment, so we got our inputs. And there are several ways to perceive the environment. So we acquire data from the environment, then we need to interpret those data. We need to reason about the knowledge we already have about the environment, and we need to process the information that is derived from this data. And so, finally, we decide on the best action to take to achieve the given goal. This is a very broad definition of artificial intelligence. As we can see, many different applications can fit into this definition. However, I asked, what does AI think about itself? So I asked ChatGPT to define an AI. And ChatGPT told me that it's a simulation of human intelligence. It performs tasks that are typically required for human intelligence, such as visual perception, speech recognition, decision making, and language understanding. And it encompasses various approaches we will talk about on the next slide. So this is the second definition we see, that in this case, the AI is compared to the human intelligence. We can argue about what the intelligence actually is. This is a philosophical question, and we can have a talk about it for another hour or two or more. So in this kind of definition, we are talking about human intelligence, which I personally don't really agree with, because there are several types of intelligence. Even the animals and even the nature, biology has its own intelligence. And actually many algorithms are based on this kind of nature-inspired intelligence. So I personally disagree with this human form, but many other definitions use it as we simulate the human intelligence explicitly. So these are two different definitions. You can make your mind, or you can take a stance, or do not need to take a stance at all. But it's nice to know that there are several definitions, because even the intelligence itself is not properly defined, and it's argued in a philosophical manner. So there are different subfields of artificial intelligence. Many of you have heard about machine learning, which is kind of the most popular currently. But there are also knowledge-based systems. There is computer vision, robotics, natural language processing, which is often associated with machine learning and deep learning, of course. And we can plan and schedule. And these are the optimization techniques, the evolutionary algorithms or genetic algorithms, which are inspired by your nature, as I was talking previously. And there are also several components of AI and types of AI. We will talk about some of these aspects in the future slides, but it is good to know that artificial intelligence is a very broad term, and it encompasses several subdomains, several types of problems, and several approaches to solve those problems. So let's take a look at a bit of a history at first. So let's very briefly go through some AI foundations. The people were fascinated by the term of artificial intelligence. Even the Greeks in several hundreds BCE discussed and tried to create mechanical object with independent movement. There were some birds like this, and they worked on a steam basis. So we can again discuss if the movement was independent, but it was definitely some moving object, which was not that practical maybe at that time, but we see that the people were fascinated by creating something that moves, something that that is independent and can maybe think of itself. Then the first coining of a term robot was in 1921 of an idea of artificial people in a book. And we still use this term robots to this day. The neural network foundations were placed in 1943 by comparing the human brain's neurons and how can we implement these neurons and this thinking into machines. And the artificial neuron was created. The Turing test, or the Alan Turing, designed a test how to distinguish between the intelligent machine and the human. So how to test the intelligence of a machine. Today's language models can successfully pass this test, but it was a huge thing to at that time to be able to distinguish maybe on a theoretical level if you are communicating with a machine or a human. Which was at the time an interesting problem. The artificial intelligence term was coined in 1955, and it sparked a huge research interest in the future. The first simple neural network, or perceptron, was created a hardware device from Frank Rosenblatt's idea, and which is interesting, we still use the idea of this perceptron to this day, as we will talk on the next slide. 1966 was the first ever chatbot and a pioneer of natural language processing. The psychotherapist is Eliza. You can check it out online. It's kind of interesting to see how it worked. And yeah, then we have the first AI winter. The AI winter means that the initial interest in research, in funding, in commercial usage died down for a while. Why? Because there were some interesting ideas, interesting concepts, but the computers weren't really that powerful back then. So we had ideas, but there was no hardware to execute them on. Then we went to 80s, which is which again had some AI boom, some research breakthroughs. We received another funding, and expert systems were kind of popular, which were kind of knowledge databases that could answer some of our queries. So something like today's chatbots, but far less robust, let's say, and far more restricted. But what is interesting, the backpropagation algorithm was invented almost 40 years ago, sorry, and we still use this algorithm or its variants to this day to train the neural networks. But what happened? We invented backpropagation algorithm, so we finally knew how to efficiently train our neural networks. But again, there was no hardware to run that algorithm on. So again, some interest died down, and there were not many interesting to be in the world of AI. But after the winter comes the summer, and maybe even more hot weather, of course. So again, the field of AI had risen from the ashes, and there was a huge interest in new probabilistic approaches, the AI agents, the machine learning concepts, data mining, and so on. There are several interesting dates in this era. For example, the world chess champion was beaten by the computer. The first commercial robot could be bought for households. It was this Roomba vacuum cleaner. And the machine learning and AI techniques were used back in 2006 for advertising and user experience and so on. And then there was a big data and deep learning, a lot of new ideas. We had the Sophia, first the humanoid robot. This was a nice achievement by Google's AlphaGo to beat the world champion in the game. It's a game which is very complicated and has many states, so it's very hard to think about the future and to predict what will happen in the game and think much ahead. So this was a nice achievement using reinforced learning we will talk about, and so on and so forth. And beginning 2016, 2017, the AI era as we currently are began. So there were many advances in generative AI, in hardware, in availability of data. The transformers were invented, which is the system for or the type of neural network or component in neural network that is used in large language models, which the chatbots such as ChatGPT, Gemini use. There were global explosion of commercial AI efforts, some protein folding by Google. Then the ChatGPT was released. That was really a chatbot hype. Several text-to-image models, new large language models, and the interesting thing is that the first AI regulation, in the EU AI Act, was approved to regulate what happens in the world of AI. So that was some history. Let's take a look at some terms, some terminology, and learn how to distinguish between the AI, machine learning, deep learning, and so on. So let's take a look at some terminology first. So we already talked about what the artificial intelligence is. So it encompasses, as we talk, several approaches to process the visual, language, audio data. It can be used for planning, optimization, and so on and so forth. But what is important, the AI itself does not necessarily involve learning. So it doesn't need to learn by itself. For example, the expert systems were fed some knowledge, and they didn't learn the new knowledge by itself, but rather they reasoned on the knowledge, and they used that knowledge to come up with some conclusions, but do not edit new knowledge by themselves. It were used just as a response machines. Also, there is a state space search, as we've talked about the Tic-Tac-Toe. It can be also considered AI, and it's not learning. There are nature-inspired algorithms and so on. So the AI, artificial intelligence, is a very broad term, but it doesn't require or involve learning new things. However, what involves learning is by the name machine learning. So the machine learning automatically learns the decision rules or parameters from the data, as we will talk on the next slides. And the most popular form of machine learning are neural networks, which are very globally used and spoken about. But we will also see that many other algorithms like decision trees, nearest neighbors, and so on exist, which also learn things, but are not as popular as neural networks. But all of the algorithms have its uses and can be used in different scenarios. And then finally, there's deep learning, which is again subset of machine learning. Again, it learns, and these are typically connected to neural networks. So these are very huge, very robust neural networks. And what is interesting in deep learning, they can determine the features or the what is important from the input by themselves. So in machine learning, we as humans need to adjust the input data with some domain knowledge to help the machine learning algorithms to learn better representations or more accurate representations. But in deep learning, it can be done automatically, for instance. So we feed the whole image into the machine learning model or the deep learning model, of course, and it automatically learns what are the important features, for example, the shapes at the picture to recognize the objects. So these are typically neural networks with many layers and specific architectures, convolutional neural networks, recurrent neural networks, and so on. And essentially, almost every AI project we came across during the past years as mere humans, as in the media, was based on deep learning. All these chatbots and creating images, processing video, processing images, creating avatars, and so on was based on deep learning. So this was this terminology. Then another important thing to distinguish the AI techniques are between discriminative and generative AI techniques. In discriminative AI techniques, we have data, as we can see. These are 2D data, and there are two different types, as we can see, two classes of data: red types of data and blue. What does discriminative AI do? It aims to learn how to separate the data in order to classify them. Here we have two classes, but it can be generalized up to any number of classes. If the decision boundary can be clearly drawn, the AI or discriminative AI can learn this boundary to distinguish between different types of data. Consider these as dogs, these as cats. Each type of animal has its specific, the shape of ears, the eyes, the mouth, the body, and so on. And the AI will try to distinguish between these the two different types or n different types. And then there is a generative AI, which is how the generative models, yeah, again, ChatGPT, image generation work. So how it or its idea is to learn a distribution, the mathematical distribution of the data, how the data were generated. So it doesn't only try to distinguish between the two types of data, but it aims to learn how the data were created. What are the distinguishing features of the data that correspond to that given type of data, and in what range those features are. So we try to learn the mathematical distribution. And as we learn this distribution, we can then sample or take a new data from the distribution in order to generate new content. And it can be used both for classification, so distinguishing new data, and generation, so generating new types of data. And then let's talk about different levels and types of AI. What we currently have is this narrow AI, and it's machine learning, which means that this narrow AI is specialized for only one or few tasks. It can typically outperform humans in these specialized tasks, but cannot be generalized. For instance, we as a humans, we can perceive many types of objects. So we can see, we can speak, that we can work, we can move, and so on. We are very versatile, very universal. Machine learning can be taught to do a subset of our properties or of our skills even better than we, but it cannot be learned to know everything currently. If this was the case, we would be talking about the general AI. So the machine learning we would have the machine intelligence, let's say, which would be at the similar or same level as we are. And then there is a super AI. Super AI means that the machines are already conscious, so they know about themselves, and they are smarter than humans in every aspect possible. So today we are currently here at the narrow AI, and it is debated if we can ever get into these two fields or two types, and the researchers are still like debating when it will become, if it will ever become, and so on and so forth. So currently the robots are not going to overtake us because they are specialized in certain tasks and are not as general as we humans are. Okay, so let's talk about some principles of machine learning. I would really start with gaining some intuition about what the machine learning actually is and how we can compare it to regular problem solving in computer science. So this is regular problem solving. We are talking about algorithm. Algorithm can be described as a set of rules that are used to obtain the expected output from the given input. So this was and still is the regular way how the most computer programs are created and how our daily usage of computers is performed. Some programmers, humans, need to specify these rules explicitly in order to achieve something. So for example, when we click on a web page, the web page opens. The click is the input, maybe the link we want to go on, and then the programmers needed to program how the web page will load, what will be the content, and so on. And after this is programmed, this input is translated onto the output and it is shown at our screen. So this is a regular algorithm when we need to specify the rules and steps manually. So in regular programming, as I said, we need the algorithm, or we want to get an output, and for that reason, we need to program an algorithm. On the other hand, the machine learning takes a problem from different perspective. In machine learning, we suppose that we have the input data and we know, or we may know, what output do we want to achieve. So we have these that we call them examples. These are the data or the X, let's say, type of data, and these are the outputs, the labels, or Y type of data, as we call them in machine learning. And what we want to achieve, we want our machine learning algorithm to determine the set of rules, the set of steps automatically. So the humans do not need to think about how to do that, but only show some examples, what is the input, what is the output, and let the machine learning model determine what to do in order to achieve such an output, which is a different kind of paradigm, as we can see. And if the data are competent enough, and if the problem is not overly hard or unsolvable, the machine learning algorithm will be able, given enough data, to determine these rules. So, to sum it up, regular programming, we have an algorithm that needs to be stated explicitly. In machine learning, we want to learn the algorithm based on the input and output pairs. And the machine learning often creates its own or hidden knowledge representation, which is dependent on the algorithm itself. So now we can define what the machine learning actually is. The machine learning, as we saw, stores some hidden knowledge, some representation of what it learned. So we call this hidden representation or this knowledge an experience E. So the computer program learns from experience with respect to some class of tasks T, an experience measure P. If its performance at tasks in T, as measured by P, improves bit experience E. Now you may think about what the hell just happened. You may pause it for a while and read it for yourself once again or twice or thrice, as I needed to do when I first saw this definition. But what it actually says is that we have some class of tasks, or we have some type of task we want to do. For example, to distinguish between those cats and dogs. That is our task. And we can have multiple of these tasks. So that's T. Then we need to measure somehow how well our machine learning model performs. If it misclassifies, so if it's the picture of a cat, but the model tells that it's a picture of a dog, it's wrong. And we needed to measure this error somehow via some metrics, such as, I don't know, accuracy, and tell the model that you are wrong. So we need to measure how the model works on tasks T, and there is the experience. So when we show the model more examples, more samples, it gains the experience. And so what does the definition says? As we show the model more examples, more samples, it improves its experience. And if the experience that it is learned influences the measure P, which is also improved, at some tasks of T, so at some specific problem, then it's a machine learning. Then it's a program which can learn from new experience, from new samples that we will show them. This is the definition. Again, machine learning has several definitions, but this one is widely accepted, but you may bump into other ones. But this is a general definition of machine learning, and it's not that disputed as the AI. Now, let's take a look about how this learning is actually performed. There are three types of learning. What I was talking about before was supervised learning. So we have some input data, or the X, as I told you, and we have some output data or some labels. How do we want the output to be, the Y? And so our goal is to find a mapping between the X, the input data, and the class Y, the output. So it's actually a function. Our model aims to learn what mathematical function to use to transform the given output to the given input to the output. And this function, the mathematical expression, is actually the algorithm that we talked previously. So, for instance, this is a classification problem. When we put this image to a machine learning model, this is an X. We expect it as to say that it is a dog. The dog is the label, or Y. So this is a supervised learning. We have input data, and we have also the expected outputs. But what if the outputs or the labels are not known, are not available? Then we achieve what is called unsupervised learning. So in unsupervised learning, we have only the input data available, but we have no labels. So logically, we cannot expect the model to tell us that these are the dogs if we never told the model what the name of the object is. But what we can do instead is to try to determine some structural patterns. So what are the similarities between the objects? What are the most common features or some most common values? So and to distinguish between different types of objects, or to group the similar objects together. This is the clustering example. The clustering creates a cluster of similar objects into one bracket or into one group, let's say. So we cannot use it for classification, but we can use it for determining structural patterns. And the very interesting type of learning is reinforcement learning, when we are dealing with an idea of an automated agent, or that we can call it a robot or some entity, let's say. And this agent is present or is placed in some environment. That, for example, when we are talking about the vacuum cleaner, the robotic cleaner, the environment which is placed in is a room. So the robot needs to know what state is it, what is the state of the environment of the room that is currently present. Then it at every stage at every state there are several possible actions that the agent may take. Still, if we are talking about the vacuum cleaner robot, the actions can be like we move, or we can turn off, or we suck the dust or the litter from the ground, and so on. And then we have a reward. We need to tell the agent that it's doing something good or it's doing something bad, and we use a reward function which can be given after each action or at the end. So how does it look like? The agent is at some state and it can do some action, and after each action the state that the agent is changes because the action influences the environment somehow. So what would be the goal of such an agent? It wants to maximize the reward that is received by the sequence of action. So again, we can receive the reward after each action or at the very end. And I already told you about the example of the robotic vacuum cleaner, but another example could be when we are sticking with animals, the automatic dog keeper. So we want to train a robot, this woman in this case, the robotic woman, let's say, which will interact with the dog, and we want to increase the dog happiness. So we want to make the dog happy. So we don't want to waste time playing with our dog, but instead we want to teach an agent how to treat the dog, so the dog will be happy and we don't need to take care of it. So we defined actions as we can pet the dog, we can feed the dog, we can send the dog to sleep, or actions we can pull the dog's tail, we can kick the dog, and so on. And the rewards that are received are like the negative reward, the decrease, which decreases the dog happiness. So we also decrease the reward of the agent. Or when we increase the dog happiness, we can also put some positive reward for the agent. And when we theoretically let these agents to interact with the environment for long enough, and give them the expected reward after each action or at the end, the agent will eventually learn how to treat the dog or what actions to do at which states in order to maximize the reward. So these are the three types of learning. Of supervised, we have the data, we have the labels. Of unsupervised, we have only the data and no labels. And the reinforced, when we are talking about some agent in the environment, and we are directing it via the reward that we will give them. So each type of the learning is used for different purposes. The supervised learning, we distinguish between the classification. We want to predict some specific class. We want to classify an object. Or regression. We want to generate some value. The classification can be used for diagnostic purposes, to classify images, as I was talking about, for detect identity fraud, and many hundreds of more different cases. And regression, when we are predicting the next value, we can use it for weather forecasting, market forecasting, expecting life estimations, and so on. Then there is a reinforced learning, which we can use for games, skills, learning tasks, navigating the robots, deciding in real time, and so on. And then there is unsupervised learning we can use for clustering, as I was talking before. So we can group objects with similar traits into the same groups. For instance, for the recommender systems, we can use it for recommending the contents or segment some customers and so on, or to reduce the dimensionality. So, for example, to visualize big data. So these are the learning types or the machine learning class problems. Okay, let's take a look at the project life cycle. How does the machine learning project ever looks like? At the start, we have some requirement, which is typically coming from business, but it can be also like government requirement. But the aim is that we want to achieve something. For instance, to increase our rewards or our profits from business, or to decrease the time that the customers are waiting for the response, and so on. So this is the requirement. Then we need to collect the data of the problem. Plus, we can annotate the data. So if we have a database of customers, we need to use this database in order to make the decisions, or in order to simulate how the decisions will be made in the real world. We want to automatize this process by machine learning, so we need those data we are using to let the machine learning model to learn. After collecting the data, we need to pre-process them. Pre-processing the data means removing some, for example, wrong values, some missing values, or the scaling the data. So we need to transform the data into more friendly way that can be used by machine learning. We can then analyze the data. We can use the data for model training afterwards. And after the model is trained, we evaluate the model. This is the important part, because model needs to be evaluated on some unknown data. The model will how the model will perform on the data that were never seen in practice. And afterwards, we deploy the model into practice and see how the model works, how the model behaves. But the point is that this process never ends. As we can see, it's a circle. Why? Because the data or the environment that the model is deployed usually changes. The customer changes their behavior, the new product is introduced on the market, and the machine learning model, when trained with the old data, may perform badly because the data are old. So this is called the model drift or a concept drift, when the environment changes, and for that we need to run the circle again. So we need to collect a new data or add some data to the existing database and retrain the model in order to achieve the desired outputs. So at this point, let's take a look on a way how can we build our own machine learning model. And we will use an example of grenades and apples, which is an example that was used by my university teacher several years ago. And this example stuck in my head for up to this day. So I decided to reuse this example. So let's demonstrate how the machine learning, more precisely the neural network model, is built and trained in order to achieve our task. So our task is to distinguish between the grenades and apples in order to properly distribute them. So we want apples to be sent to children and grenades to be sent to soldiers. So, what is the process? As we recall from the graph before, firstly we need to collect and annotate the data. So we do precisely that. We collect several hundreds, even thousands of images of different grenades from different angles, different types of grenades, and apples as well. We can take photos or we can measure their weight, their colors, and so on. And we need to label the data. The labeling is done by assigning that this is a grenade, this is an apple. So in our case, we split the label data into two groups, as we can see. And afterwards, we pre-process the data. So if there are any images or any measurements that are wrong, for example, the image doesn't contain any grenade or any apple, then we remove it from the dataset. So this is the pre-processing. Then we initialize our AI model. Since the model was just initialized, we called it a dump AI. The model is very dumb because it hasn't seen any data yet. So it couldn't learn for now. And how does the training work? We let the model to classify one object. Let's say it's one apple. We let the model classify one apple, and since the model has never seen any apples nor grenades before, it will spit out some probably random numbers or numbers that are like close to balanced probability. So the model will never tell us the precise precise answer, but only a probabilistic answer. This is an apple for 47% because it should go to children, and this is a grenade for 53% because it could be sent or it should be sent to a soldier. So in this case, the model was wrong, and the soldier would be throwing apples instead of grenades, which is of course wrong. So what do we do? When the answer is wrong, we need to correct the model. So we need to have some corrective or feedback function to let the model know that it was wrong. And the correct answer was 100% apple, 0% grenade. So we let the model feedback, and now the AI or our model is less dumb because it has seen some example, and we showed him how how it should look like, or how the example should be treated, what should be its output. Now, what we do is we let the model classify another object. Let's say it's another apple. Now the model says that it's an apple for 69% and 31%. Why? Because the model has seen only one apple before and 0 grenades. So now the model will think that, yeah, I've seen one apple. This looks kind of similar. It should be an apple. So let's send it to the children. It's correct. But again, we want there to be 100% and not 69, and we want there to be 0%. So we again provide some feedback to the model, which is now smaller because the answer was correct. So again, the model learns, and the AI is suddenly even less dumb. Now, let the model classify one grenade. Again, we see that the model thinks that this is an apple. Why? because the model has seen only 2 apples so far, and it has never seen any grenades. So the model thinks that I've seen 2 apples so far, this will be another apple. Okay, it will be an apple. So the model thinks 74% for apple, 26% for grenade, which is wrong. So again, we do correction, we do feedback, and the model learns, and it's even less dumb than before. When we do this hundreds or thousands or even tens of thousands of times, the model will get competent and will know what are the distinguishing features and would be able to classify the 2 classes with a precise manner. So we repeat this for the whole dataset and allow the model to find patterns. And which is important now, we need to evaluate the model on unseen data. So we use images or some data objects that were not seen, that were so-called holdout before, and we use them to evaluate the model. And if we are satisfied that this is okay, then we are happy and the model is good. So we've seen that the model relies on the data heavily. What is shown in the data, what labels are there, the model completely takes it over and learns from it. So the data are very important. The machine learning algorithms do not understand the semantics of the data. They don't know that this is an apple, this is some like food, we should eat it, and so on. They're only learning some patterns, only learning to distinguish them and what features are similar to what I've already seen before. So they will learn what they are told to. If we tell the model that this is a grenade and this is an apple, it would learn that because it will not think that it can be different or it can be flipped. So the model does not reason, does not think, does not know the world. What data we will give it, that the model will learn, which is a problem because we can see the data affect every stages of machine learning pipeline. So when we collect bad data, the model will get affected. When we extract wrong features from the data or not good enough features, again, the performance will be affected. Bad preprocessing will affect it, and so on and so forth. So the data are crucial in every step of machine learning. So we need to verify that the labels are correct, the data are clean, there is no bias. We will talk about what's the bias on the next slide. And the distribution is sufficiently covered. So we need to verify the data. So let's talk about this bias I was briefly introducing. What is the bias? The bias basically is that the model will learn some feature or something that correlates with the output, but is not necessarily the cause. Let's consider a gender bias, and there was an issue with an Amazon automated resume screening that was discriminating women in 2015. Why? Why does the machine learning model think that the women shouldn't be approved for Amazon? Well, Amazon is a technological company. And when we are hiring the programmers, 95% of all CVs or 90% of all CVs of our resumes are men. So it makes sense that even if the women are same or even more competent programmers than men, still there will be 9-to-1 ratio of men accepted to women accepted. So when the models see this statistic, yeah, there is a 90% chance that I will accept the man. So let's prefer that and let's create this gender bias and automatically discriminate women because statistically it's correct. Like the model will not lie the model will learn exactly what's in the data. But these hidden patterns in the data may be wrong or may be discriminating. Of course, there is a racial bias when a lot of society in America, according to the study, see African American males to have like an ethnic stereotypes to be dangerous criminals. Of course, when the machine learning model sees articles or some social network posts that are introducing or even reinforcing this bias, the model will learn it. And then there was, for instance, another case with the Tay on Twitter, which was the AI chatbot from Microsoft, and it learned to tweet like racist and sexually charged content based on the Twitter interactions because the users fed it with with such messages before. So the bot needed to be shut down 16 hours after its initial release because it started to be racist and sexually charged. Because people gave him that messages, so the bot learned. Okay, what's the current state of the machine learning field? So the massive improvements in the generative AI and deep neural networks were made in recent years. And we can ask, like, why now? What happened? What was so specific about these past years? The extreme amounts of data started to be available. Internet and computer network started to be faster, more people connected, more people shared contents, more websites, more social networks. So finally, there was enough data to use. Of course, the new algorithms came, which were even more efficient, have different architectures and data representations, so they allowed to make use of these huge amounts of data. These were the transformers on the generative models and so on. And finally, also the hardware improved, which allowed to store, transform and process all this data that were created. Actually, the machine learning is run on GPU graphical cards or specific TPU cards, which have gotten much stronger in the past years. Okay, let's talk about some machine learning under the hood. So how does the machine learning actually work from the slightly mathematical perspective? Okay, so if you remember the perceptron that I was talking about from the 1957, well, here is the same perceptron 65 years ago, and it's still used. It's one neuron that is used as a part of the neural network. So this previously was the hardware implementation. Nowadays, the neurons are used in software. So what is this neuron really? This artificial neuron is supposed to simulate the human neuron in our brains, and it's supposed to process some kind of information, some kind of input, and recognize which input is important with these weights. So let's break it up. We have an input composed of x1, x2, and xn features. These are some numbers. Could be rational numbers, could be like integers, like but typically a very small numbers that are scaled from -1 to 1, and it is range, something like that. So we have an input, let's say, that is representing some object, for example, a 1 pixel or several pixels from the image. Then we have some weights, and these weights are telling us how important is the input and how does it influence the output that is expected at the end. So these weights, if the weight is 0, as we can see, we are multiplying weights with the input. So if the weight is 0, it will completely turn the input x to a 0. If the weight is a big positive number, it will put a positive impact on the input. So the input will correlate positively with the output, what is expected the output value. And if the weight is negative, then the input will negatively correlate with the output. So what we do in this neuron, we run the multiplication of these weights, of these x's or the inputs, and sum it up. In order to be able to have more robust representations, let's say, we add a bias or B to the neuron, and that's it. And then we need to apply some function G, which is nonlinearity, to be able to represent, again, more robust or more complex relationships. So here we have our neuron, and as you can see, it's just a mathematical function. Application of this nonlinearity function G, which is some function we don't need to discuss or to dive deeper in. And this is what happens inside the neuron. So we get inputs, we weight the inputs importance, we add some other number, and then we plug it into some function and we have an output. As we can see, for n x's, for n inputs, we have n plus 1 trainable parameters, which is important that these weights and this bias can be learned, or these are the parameters of the network that are trained. As we show the network or the neuron more samples, the neuron will adapt these weights and this bias to better represent the expected output. So this is changed, this is learned from the training. And so suppose these B and weights and X are just some small numbers that can be positive or negative. So when the training is actually going, or when the training is happening, what the model is doing, or the perceptron is doing, it is learning how to distinguish the data. We can see that the learning is performed in iterations. So we show the model all the samples and let it update its weights and bias. And as these weights and bias are gradually updated, the model will learn how to distinguish between the red data class and the blue data class. Now, when we put several of these neurons together, we achieve a neural network. This is a very simple neural network with 3 inputs and 4 neurons. As we can see, again, there are some weights. Now it's not a vector, but it's a matrix of weights. This is the vector 1, vector 2. They are together are matrix, which is a fancy mathematical term, let's say. And they have, each neuron has its bias. They produce the output, and the output goes to another neuron, which again weights output of other neurons and adds its own bias, and so on and so forth. So every neuron does this function, but when we put many hundreds, thousands, tens of thousands, even like millions of neurons together, we achieve many trainable parameters which can learn very complex mathematical functions. And these functions are then used to describe the data, to create a decision boundary, or to decide how the model should act, or to generate a new data. So this is a function that this neural network is using. I'm not going to torment you with that, but again, this is the final output of the network, and it's considered of these functions, these weights, and we just use them to process the input. So yeah, we see very simple network, 3 inputs have 16 parameters. now the network are visualized like this. There is a number of neurons in the layers, and as you can see, there can be several layers in the neural network. The deeper the network is, the let's say more complex behavior it can learn, but also it's much harder and much more expensive to train. And of course, the number of these layers matter, but again, there is different number of neurons that can be used. So we talked about several parameters uh, in the previous networks, but what do modern networks have are actually billions of parameters. This is the visualization for large language models. As we can see, as the number of parameters grow, the models tend to learn more things, from simple language understanding to answer some questions. They can learn how to summarize the text, how can translate the text, how to, I don't know, explain the jokes, or some reasoning, and we can have a dialogue, and so on and so forth. So the number of parameters definitely matters. And as we can see on these newest models that were released recently, these are all the language models, that some models have several hundreds of billions of parameters. GPT-4 is rumored to have like 1.7 trillion parameters, and the newest Claude 3.5 is rumored to have more than 2 trillions of parameters. So really huge models that takes weeks and months to just train, to set these parameters right, and costing extreme amounts of money to run. And yeah, from these concepts, I would like to stress out that the machine learning is not just the neural networks. I talked about it before, but let's have a brief look at another machine learning technique, which is called the decision trees. So let's suppose we have a task that will help us if we should play a game or not, based on the weather conditions. So here are the features or our inputs that we have, like the weather, temperature, humidity, wind. And here is the result if we play the game. This is our label. This is our why. So we want to create some decisions if we play the game or not. This is a very simple example, but and for simple problems, we don't need to use heavyweight neural networks, but often more lighter models, such as decision trees, are sufficient. So when we run a model, the algorithm on this data, this is what happens. We have this input data, and the resulting machine learning model will create this reversed tree that, as the name says, can help us to decide what to do. If the weather is cloudy, we always play the game. Let's see on the data, cloudy, we play. Cloudy, we play. Cloudy, we play. Or if the weather is sunny and the humidity is high, we don't play because the conditions are not great. So again, the weather is sunny, humidity is high, we don't play. But if the humidity is normal, then we play, as we can see, and so on. So these are the very simple models that can help us to decide to create some simple decisions, and they can be useful in different scenarios. For example, when we want something lightweight, something that can run in real time, or interpretability, explainability is also a huge problem, because in classical neural networks, the explainability of the model decisions may be problematic. It's also a research direction how to explain the decisions of neural networks and what are the influencing factors that help to decide on the final output. But in more simple models, these tree-based, decision tree-based models, our explainability is very trivial, and even the human can tell how the model will react, how the model can decide, which is very interesting and necessary in certain applications, such as the cybersecurity I work at. We need to know why model behaves as it is, so we can use different types of models. Okay, so these were some basic concepts, machine learning under the hood. Of course, knowing the whole algorithms isn't, or all the math is not necessarily that I was showing you before. But the point is to understand that it's not the black magic. It's based on some mathematical equations and mathematical problems and statistics that, when solved correctly, can help us to achieve the machine learning that we are talking about. Now, let's take a look on the modern generative AI and to learn how these generative AI models work. So, we were already discussing this, what the generative AI is, of the idea that we want to learn the statistical data distribution and then sample from the distribution. So other names for the generative AI is the generative artificial intelligence, generative AI, maybe GenAI or the GIA. I've never seen this, but if you do, it's meant for generative AI. So most of these practical or hyped applications nowadays are from the generative AI because they are finally practical for our humans. We can use them as assistants, as someone who can help us to brainstorm or to be creative. But most practical applications before 2020 approximately were focused on classification and prediction, but after these ChatGPT language models, the generative artificial intelligence have received a huge attention in the media and not only in a research domain. So the generative artificial intelligence were moved by several advancements. There were the generative adversarial networks and the variational autoencoder research topics, which were designed back in 2014. 2017, the core of all large language models, the transformers architectures, were released and were discussed. But as we can see, it took several years for the industry to actually incorporate these transformers models into some practical solutions, such as the ChatGPT or Gemini or other models that we have heard. And 2021, the stable diffusion, the model based on diffusion was released that can generate images. We will talk about it in the next slides. So let's take a look on these large language models, what they are and why should we care at the first place. So large language models, or LLM, as they are commonly said, is not only model, but the LLM is composed of the data that were used, of the training for the given data, and of course the architecture of the model. So the architecture was trained with the given data. That's the large language model. Because the training is very expensive, it can take, as we can see, thousands of hours on the large data, then having only the architecture is not useful for basic humans, let's say, because we cannot afford to train it. But once the weights of the models are known, the model is trained, then it's becoming interesting and it's the large language model. So the data is a very large corpus of data. We usually say that these large language models were trained on the whole internet, because what the engineers and researchers did, that they downloaded thousands, tens of thousands of web pages and their contents, for instance, like the Wikipedia articles, and they used these articles to train the large language model. So we are talking about the petabytes of data, so 10 to 15 bytes. And just for illustration, 1 byte is 10 to 9 bytes, is approximately 180 million words or 78 million words. So we can imagine how many words were used for training when the data are of petabyte sizes. Okay. Then the architecture is typically a deep neural network that is based on transformers, which is a component of neural network. We will not dive deep into them, but it's a very important technology for LLMs. It's a core of LLMs, but the architecture is just a neural network that we've seen before, with the neurons and with some specific components. And the training of the large language models consists of a pre-training and fine-tuning. Pre-training is this general purpose training, considers of thousands of hours, tens of thousands of hours on these large data corpuses. But after pre-training, the model is basically acting as just a word completion engine. So it can generate words, but they cannot be really useful for what we want. So the fine-tuning of the LLM models happen, which is adapting these models for a specific task. For example, to answer our questions as a chatbot or to communicate with us. Then our task of these large language models will be to generate the next word based on previously seen words. So this is how the large language model work. They seen some previous words and they want to generate the next word and then the next word and next word, and this is how they generate the text. We will see in the next slide again. But then we need to think about how do we generate this text. Well, it's based on probability and statistics. That the mathematics is the core of machine learning. And yeah, the LLMs are base of currently popular chatbots. So let's take a look at this. How does the text generation work? How the models are trained and what are they expected to do from this next word prediction? So just for the context, the models are not actually generating the words themselves. The words are translated into numbers because yeah, it's still computers. They worked in a binary with binary numbers, so we need to translate them into tokens, and these tokens are translated to some numbers or encoded into numbers. But this is just a side note. So the models are not working with words, they are working with numbers, they are working with some tokens. So the pre-training of the models is based on predicting such a next token or the next words of the text. So how does this work? The model aims to create some statistical map and then to map the probabilities of words given the context. So how do we train the model? Let's consider this this simple sentence. My red shy mouse scared the horse. First thing is to tokenize this sentence. So what the tokens are representations of words, and also a very specific thing is that we want to add some starting tokens and ending tokens, which can be placed at the end of each sentence or at the end and start of the prompt. So the model will know that that it will learn actually some syntactic information and additional information about the structure of the sentence or the structure of the word prompt. So we tokenize the sentence, we add this starting and ending token, and as we can see, there is some numeric representation of each word, which is like an encoding of the tokens into some numbers that the large language models can work with. And then we prepare for training. So we split the sentence into several subsequences, let's say. The gray is left out, it's not used. The green is the context the model is given, and the purple color means the next word we want to predict. So the model is given a context start and a next word of my. Then, this is one training sample. In another training sample, the model is given the first two words as a context and next word as red to predict. And we repeat this for the whole sentence. So each time we increase the context that the model is given and what next word we are or the model is expected to predict. And when we do this for each word hundreds of times, hundreds of thousands of times, or even like millions of times, the model will learn the syntactic representation of the given words. So it will learn that my can be at the start of the sentence, can be in the middle of the sentence, and it usually ties to some noun and so on. So the model will learn these syntactic rules according to processing a huge number of such tokens in this way. So it will be later able to predict what will the next probable token will be, as we will see on the next slide. So now when we pre-trained our model to generate next word and next word and next word, let's see how the text generation actually works. So this is the generating the text. We are no longer training. We use the model to predict the next possible words. So we use the model to generate new text, and how it is work. The model processes the context that it's given. Then it predicts the next word based on that context. It adds the next word to the context and repeats. So by this rule, it simply keeps adding new words at the start of each sentence and at the start of each the contextual block, and so it increases the context and creates new words. Simple. So how does it look like? This is actually a sentence that I've taken from ChatGPT output, so it definitely generated something like this. So the versatility and capability of LLMs make them valuable tools in both personal and the model should fill some missing words there. So this is the example of how can such of the probability map can look like. There can be a word or, there can be word and, word circumstances, and so on, like thousands of more words. So what the model will do, it will evaluate the probability of each word. And as we can see, the word and has the biggest probability in this context because probably the model has seen the word both. And when it sees both, then like or and would be probable to continue as the next word. So it generates the word and adds it to the context and runs again. So at this context, it is processing this sentence, valuable tools in both personal and the next word needs to be filled. So again, it looks to its map, and at this case, it again has some map with some probabilities, and in this case, the professional seems to be the most probable word, so it's generated and added to the context, and that's what we can see on the screen when the LLM model is talking with us. Now we can think about how these various strategies to pick the token can be used, because if we only use the deterministic strategy, or the strategy that we pick the most probable word every time, what can happen is that the model will start repeating itself, because it would be probabilistic. When it sees some contexts, it would always generate the same word, the same continuation. So the generated text may be a bit blunt. So what the ChatGPT and other models are actually using are the stochastic strategies of generating the next token. So they don't always pick the first most probable word, but there are several strategies. For instance, they pick 5 most probable, and from these 5, one is chosen randomly, and so on and so forth, to not make the output seem so blunt. So as you can see, if we use the same prompt several times for this large language model, the output is different every time. If the deterministic strategy was used, the output would be the same. So we want some diversity, so the stochastic methods are usually used. And now we see the problem of hallucination. You may have heard of hallucination. If not, that the hallucination represents a fact that the large language model is making up the contents, is making up the facts that are not necessarily true. It can tell you about the historical events that never happened. It can pretend that it knows what it's saying, but in fact, it may give you a bad advice or bad answer, which is incorrect if fact checked. So this is hallucination. And now we see how this hallucination can happen. It's always some probability, some statistical map. So the model cannot really understand 100% what it's generating, but it understands that I need to pick some next word. This is the most probable, or one of the most probable. So here we go. And I don't really care if it's truth or not. So this is the problem of hallucination, and it's still a widely researched topic nowadays, even when it's known for years. And there are several techniques to prevent or to reduce the hallucination, but still the models that we use nowadays, the ChatGPT, the Gemini, the Claude and so on, the hallucination cannot be fully prevented. So we need to think about the outputs that the models gave us. This is just a very brief slide that what happens after pre-training. As I was in a ChatGPT case, as I was talking about, the pre-training just gives us some base models that generates some text based on the next word. But if we want to make the model usable for practice, we need to fine-tune it for a given purpose. So the ChatGPT was fine-tuned with these questions and answers. They included some human labor, so there was some labor via the supervised learning, but maybe they downloaded from some questions and answers from various forums such as Quora and so on. But the fine-tuning is done in a supervised policy. Then what the researchers did, or the engineers of the ChatGPT, they trained another neural network, which was called a reward model, that was tasked to rank the top n or the top first answer, or ranking the answers of these LLM models. And so they use these reward models as a feedback in the third step for the LLM. So what was the whole process? The LLM was given some prompt, such as write a story about frogs. The LLM did us some or created some story, but it didn't create only one, but several of them. And this reward model then sorted the best stories from best to the worst, and gave the feedback to the LLM model to improve its generation capabilities. So as we can see, the all types of learning, the unsupervised for this next word prediction that we talked before was used, then the supervised, and finally the reinforced. So these methods are not exclusive, they can be used within one machine learning solution together. Okay, let's just give an example or of an idea of the diffusion models that are popular and used for image generation. So diffusion models are text to image models for realistic, high quality outputs. They aim to learn the mapping of the desired object and the distribution of the noise. So this is more magic to me than generating the text. So let's see how it works. Firstly, we give it some picture. This is some picture of a cute dog, and then we are adding a random noise or Gaussian noise, as it is called. This random noise is basically this some random pixels, the random values of pixels we see in some interval, and it doesn't really represent anything. But as we continually add the noise to the picture in each step, so this is a picture without noise, there is some noise, a bit more noise, and as we keep adding the noise, the original picture will become the noise itself. And the task of the model is to learn how these steps influence the original image itself, and how to map this original object to the noise. So when the model sees again hundreds or thousands or tens of thousands of cute dog images, and then it receives a noise like this, based on some score function, it starts to reconstruct this noise onto another cute dog image. And the idea is that such a dog, such a picture, may have never been seen in a training data before. And it is interesting because we can actually combine several different types, let's say, or several different prompts. So we can draw a dog, for instance, with a sword, and so on, from the reconstruction of the noise. If the model has seen any sword in the training data and any dog in the training data before, we can make it to reconstruct a dog with a sword. So an image that is completely original and was never seen in the training data before. So again, how does this look? This is an explanation of the stable diffusion. If you want to learn more, I recommend to check this Polo Club GitHub.io webpage. So how does the diffusion model work? Firstly, it's a text-to-image model. So we give it some prompt. Make me a cute panda playing the guitar in a bamboo forest. This prompt is processed in a text representation. So again, tokenization and some encoding into numbers, because the models do not work with words, they work with numbers. And after this tokenization and creating some representation, it is fed to image representation refiner, which is in the first step fed with some random noise. So this is some kind of random noise that it has been given, and the image will slowly try to reconstruct such a noise into a picture that closely represents the prompt it has been given. So after the first step, or after the first time step, we see only the noise. But after several iterations, this is 15 iterations, we can already see that there is some panda in the background, but it's still very noisy. 30 iterations, the panda is much more clear. And finally, 50 iterations, we can see a panda with a guitar in a bamboo forest, according to our description. So it is very probable that the model had never seen an image with a panda playing a guitar, but it probably seen a panda, it probably seen a guitar, and it's seen a bamboo forest. And based on this information, it could combine this knowledge into a one picture generated from the noise. So personally, to me, this is more of a magic than anything we talked about previously, but still it is based on some mathematics, based on some statistics, and it apparently works, and it works very well. So yeah, these were the generative models and the models that we talked about. Let's talk about some societal impacts of these generative models, because everything has some impact. With the great power comes some some impact, definitely. So the first impact that we can talk about is the hallucination that we were already discussing. Can we really trust the information that the models are giving us? The people may be easily misled into believing to something that is false, caused by the hallucination. The models can create deepfakes. Deepfakes are images or audio or video recordings that are not true but look very realistic. If you didn't see, this is a deepfake of a pope in a very expensive jacket. This is not true. This was generated by an AI model. And this can be a problem because people again wouldn't be able to recognize if the image or if the audio recording is truth or is a deep fake. Again, intellectual property may be in danger because the models were trained with some content that may have been copyrighted, or and the authors that may be hurt by this. For instance, consider an author which uses a very specific style of painting or of creating music. And if the model is fed with this author's data, with this author's outputs, the model will learn how to simulate or emulate the author's style. And the model will be able to create very similar content as the author does. And this is the problem because the author will suddenly or could lose the job thanks to it, or many falsificates can be created by the model and so on. And also the environmental impact. So the training of the models and running of the models costs thousands, tens of thousands of hours of computation, and we can argue if this is a well-spent emissions or not. So definitely the impact on the environment can be very negative. Let's take a look at some future, like what will the future advances in the AI field be? So we will definitely have more models and bigger data, more parameters, training the models better, which result in better results and more robust results. Definitely we are heading there, but the more parameters is not the only way. Also, more efficient training and usage of the models is developed. This is called low resource models. So the models that are not using very much resource, not very much parameters, but we still want to achieve very quality results. So this is another research area. We will be also seeing more multimodal, multilingual advances. We can already see that the ChatGPT can, or the Gemini can process the image and text at once. So we can upload the image and it can analyze the image for us and so on. So definitely we will see more of it. It will be more robust and better. The models will be able to reason and to plan better. We will be able to combine the symbolic or human readable problem representations with machine learning, which is essential for the for models trustworthiness and explainability. So definitely advances in AI regulations, as we talked about the AI Act in Europe, the more regulations will need to come, and there are risks of misuse of generative AI, and yeah, some misuse has already been done and definitely will be done in the future. This is the graph of the experts' prediction of probability of the human level of machine intelligence. So basically, when the machines will be conscious, or when the superhuman AI will be a reality. As we can see, according to predictions from 2023, more than half of the experts believe that this will happen in 2050, and almost a quarter of experts believe that this will happen in 2100. So it will be interesting time to be alive, definitely for people to see how the technology will grow. And when we are talking about the impacts in the longer term, let's take a look at some longer term impacts. Like we can be victims, or that we can see a social economic transformation. Definitely, let's call it this way, because the AI already augments or completely replaces some kind of jobs. But we cannot look at the issue only from the negative perspective, because the AI will definitely create more jobs for the people. It will transform the same as the technical revolution did. But despite the technological advances, we work more than ever. So will this trend change in AI? With AI, we don't know. Will we be able to work less in the future and to enjoy our more time, our free time more? This is a question. Also, the AI can shift the inequality of geopolitics, because the AI-powered nations, which will be even smaller, will be able to compete with bigger nations, which will have similar or weaker AI. Yeah, and so on. So this is another long-term impact. There will be, and there already are, several industries that are benefiting from AI applications, such as science and healthcare, education, finance, and so on, military, cybersecurity. Like the AI will be and already is applied across different industries. AI will also allow international cooperations because we will have access to real-time translation, and AI agents may make deals on behalf of us, on behalf of humans. But on the other side of the coin, the AI will definitely or could definitely be misused in conflicts, such as these AI-based weapons, robotic soldiers, and so on. So this is an interesting impact, definitely. We already talked about the processes of decision making and to thinking about how the informations are created. So the AI will only will definitely have an impact on this process, because we will be needed to think even more critically if the information was created by humans, by AI, is it truth or not, which is already problem nowadays thanks to social networks, but it will be even harder in the future because the AI generated content will look realistic or more realistic, and we wouldn't be able to tell if it was created by AI or it is a reality. So definitely this is one impact, and also influencing the humanity future and the humanity values. There are several historical advancements like firearms, agriculture, industrialization, and many experts think that introduction of AI is another historic advancement that will shape our future and the humanity as a whole. Okay. So this was some theory, some more theoretical thoughts about the potential impacts, the potential, what can the AI be, what can AI influence, and what can happen in the future. And now let's take a look at the end at some practical examples, so you will understand that how does the current AI look like from the technological perspective, and the second example will be focused on prompting ChatGPT or other language models and how can you use them for your purposes. So let's take a look at this example of handwritten digits classification. This is a very classical problem. It's old, more than 10 years, maybe like 15 years, or I don't know. It's very classical problem in machine learning, and it's nice for visualization. How does the classification work? So our task will be to classify images of handwritten digits. The images look like this. They are very nasty because it's only 8 to 8 pixels, so very small images. But as a humans, we can tell that these are some numbers, and we can somehow read what do the numbers represent. So we will want our model to determine if these digits, or to classify these digits from 0 to 9, to do it automatically, which can be useful for instance, for reading some documents and to translating those documents into computer. Of course, we have much more sophisticated methods than I will show you today, but this is supposed to be a very brief example to show you how the machine learning looks like from the perspective of code. So what will be our process? We will load and prepare the data set of these digits. We will select the model and train it, and then we will determine the model performance on an unseen data. So let's start with this example. I may zoom a bit more. I think it's okay. So currently the environment that I will run is preparing, so we are connected. So this is just some basic imports. in programming we need to, or we can import some libraries, some modules that will speed up the work of us. So I will be using these several modules. We don't need to dive deeper into that. Let's dive deeper into the machine learning thing. So the first thing, we will load the data and briefly analyze them. We can load the data with this simple command. In practice, the data that would be loaded and collected over much longer time period. But since this is very popular data set, very popular way of a problem, the already prepared data are available for us. So we loaded the data. Let's see the shape of the data. So what will be the data that we will be dealing with? We see that there is almost 1,800 different data points for us, and each data point has 64 features, so 64 values. And if we remember, this corresponds to 8 times 8 pixel images. So each pixel is represented by one feature, by one number. We will take a look on what are these features, and we see that there is this number of entries, and these are the names of the features. So there is a pixel 0, 0, which will probably be the upper left corner, and we will slowly go with other pixels. So there are other features and they are called pixels. In IT, we index, or in technical, we index from 0, which is contradictory to natural way of thinking, starting with 1, but we start with 0 because we are weird. So just for you to understand, and how this data actually look like, we talk about it is some kind of number. So here are first 5 data points that we have, and these are the values. The value is 0, the value is 5 or 9. So I don't know precisely, but my guess is that the 0 represents the white color, and this is the amount of black. So this will probably a black pixel, and this will be something like a gray pixel. It's my guess. It may be completely reversed. So, but I think this will be the case. So, yeah, this is the analysis of how the data point looks like, and we can now count of what are the labels, how many of each numbers do we have. So we can see that the number 3, the label 3, is represented 183 times, and the value 8 is represented 174 times. So approximately we have around 180 images from each class or from each type of a digit. So let's just plot about how these images are looking. This is the code for plotting the images, which I already prepared prior to this video. So we've seen this already on the slides. These are our images, 8 to 8 pixels. They look like this, so our model will have to decide what to do with it. So this was a part of data loading and the part of some data analysis. Of course, in practice, we can analyze the data much more, not only visually, but also see for some other statistics and other properties of the data, but this is not necessary for this example. So these were the data. Now let's prepare the model for a training of it. So yeah, what we first need to do is to split the data into training and testing parts. As I was talking to you before, we need to evaluate our model performance on yet unseen data. these unseen data are called testing data or test. And so we will split this data using this function and use only training data for training and testing data for actually evaluating the model performance. So we receive the train X and train Y and test X, text Y. X represents the digits themselves, the pixels, and Y represents the labels, so 8, 9, and so on. This is used for deciding what's the true label or what's the true value of the pixel is. Now we need to prepare the data. So we need to scale them because most machine learning models work best within the close range of numbers centered around 0. So we will scale, we will reduce the values of these pixels to be centered around 0 and have some standard deviation of 1. Which is just a term of transforming the data to our models perform better. So we transform the data right now, and let's create the model and train it. So we create the model, which is the MLP classifier, which is basically a neural network we were discussing before, and I specify that it will have one hidden layer with 32 neurons, and we will use 250 iterations. So each data point will be run 250 times, so the network parameters will be able to be tuned properly. So we initialize the model, and this command model fit caused our model to train on the train data, which were scaled, and the train labels that we provide. Okay, so our model is trained. Let's predict how the model works on the unseen data. We see that we use this test X, which are unseen data. So let's do some predictions. And at this point, we have predictions at this variable breadths, and we can print how the predictions were successful. So here are the results for each class. These are some metrics of the precision, but we can care about this accuracy, which we can see is 0.98. So 98% of all the training data were predicted correctly. As I was talking before, the models work with probability and they rarely provide 100% accuracy, but there are always some mistakes which we need to account to. Of course, the models can be tuned a bit to minimize these mistakes, so we can change the model architecture, or we can look at the data and enhance the data, or we can use completely different model, which is called the hyperparameter tuning. So tuning the model, the model parameters in order to achieve better data. So yeah, but our current model achieved 98% accuracy. We consider it sufficient, so let's move on. And so let's print the predictions, how our model actually decides on some data. So these are the data from the test set that were used from the model. And as we can see, the model received this image. I don't know what it is, but the true label is 1, and the model also predicted 1, so model was correct. This is clear 0, this is 9, and this looks also weird, but the 1 is true, is predicted. Okay, so our model works pretty decently, pretty decent. We see that it is working well and it is predicting something, yeah? Now we can see some mispredicted numbers to analyze where our model made some mistakes. So again, this is some code that we compare or find out which were the misalignments with our predictions and the actual true labels. So as we see, there are 10 mispredicted labels, and let's see how or what these mispredictions look like. So this apparently was 8 based on the data set we have, and our model predicted this is 1. We can't really blame the model for this because this is really weird. This is 0. Our model predicted 6, so this could be better. This is 8, so again it looks like a key or something. So yeah, now we can analyze how the model behave and why does it behave as it does and so on. So this was the brief example from the code perspective of how can a very basic, very toy machine learning application looks like. There were only several lines of code. In practice, the code can get much bigger, much more robust, but this was very a toy example for you to see that there is some code behind it, and usually the machine learning is done by programming, but already there are software that we just plug the data in and it will spit out the results of machine learning without any necessity of programming. And this is also a possibility. Okay, let's look at the practical example number 2, which is called prompting chatbots. So how can you use the ChatGPT and all the large language models like Gemini, which is also free and pretty well performing based on my experience, for your own purposes? So you probably know Googling. Yeah, we need to find some term, so we typically write some very short Google term because we can't be really specific if we want to find some what we are looking for in Google. So we tend to be rather short, and the specificity cannot be really used for Googling. On the other hand, the chatbots, as we looked at them before, they like context and descriptiveness. As we have seen how they work, and they work based on the context. So the more context we give it, the better. So as we can see, like this is an example that what I used at ChatGPT, but we can definitely use it as well. Let's zoom it a bit, and yeah, this is the same example that I used at my presentation, and I asked the model to brainstorm 10 nicknames for a philosopher or philosopher colleague, for a colleague which is philosopher. And we see that there are some, some philosophical maybe names or these nicknames based on the presentation or the prompting that I've made before. It assigned some names of the famous philosophers in the past. But if we use context and descriptiveness, we can achieve much better results. So what we can do is to use this prepared prompt. So we don't want this very short 10 nicknames philosopher colleague, but we will give them some context. We will want to assume the role for a model. So you are a stand-up comedian. Brainstorm 10 nicknames for Johnny. Johnny holds a PhD in philosophy, works as a junior researcher in artificial intelligence ethics and human values. He likes to sip coffee, play video games, and is always tired in the morning. So as we can see that there is much more context and the model has more information what nicknames to generate. So let's see what will it give us. Caffeinated cogito, sleeping scholar, PhD, pretty hilarious dude, and so on. Like you can see the model is trying to be funny because we asked it that you are a stand-up comedian. We gave it especially 10 nicknames. So we gave it some prompt of the scope of the reply, and we gave it some additional information about the colleague that could be used to brainstorm the nicknames. So yeah, the more information we give to the model, the better it will behave. So and this was for prompting the models. Also, when we want the model to reason, to give us some explanations, we need to ask them. We need to ask for explanation, ask them to perform a step-by-step response or the step-by-step computation, and the models tend to get better results when we ask them to reason their outputs. Why? Because again, they work on the context, and if they see some context before how they are basically thinking, they can generate better results because they basically generate a good context for itself. We can talk to the model, give it more information, ask for details. I showed you in the nicknames. Section, we can have it assume an identity. This worked for ChatGPT 3. I think it's still fine for ChatGPT. I haven't tested in other language models, but having it assume an identity of a stand-up comedian, mathematical teacher, whoever, might help you to get a better results. And of course, we should or we can specify the length of the answer, style of writing, ask them for sources, so additional information. So this is the same example I've shown you with a different name of the colleague, but yeah, the results are also better for the nicknames. So that was some practical tip, some ideas about how can you use the chatbots for your own purposes. You can create content typical for social networks, emails, blog posts, description of products, and so on. There were tons of different articles you can get an inspiration from. So definitely writing, content creation, even presentations. Probably the AI would be able to generate you similar presentation that I've been putting up several days together. So yeah, try it, use it, play with it. It can really simplify and augment your work and make it better and more efficient. We can use chatbots for translation, for proofreading the documents, grammar check, or editing. I sometimes use it to when I need to shorten my paper to some extent. I ask the model to shorten the paragraph, and if there are any good ideas of shortening, I use them and rewrite the paper based on it. We can use it for computer coding. There are already several assistants for computer coding. Teachers can use them for grading essays, businesses for market and audience research, and we can have a personal fitness coach, a language teacher, a philosophy discussion partner, and so on. So yeah, there are endless possibilities. In another example, I asked the model to assume the role of a philosopher, Marcus Aurelius, the Stoic philosopher, and I had a chat with him. I asked him what is his opinion on life and death, and as we can see, the classic Stoic response that the death is something not to be feared, but rather a natural and inevitable part of existence. So we can have even such a philosophical discussions with large language models. But it's not only about chatbots. As I said, there are tons of different options we can use for the image, video generation, even music generation, generating of logos. So yeah, poor artists and designers, the AI will overtake them, and if not, that they are using the AI to simplify their work already. So nice balance. There are several pages to or the web pages to generate your images. I've been using this Dream Studio AI throughout this presentation, and I will give you also a very brief demo on this Dream Studio, which can you use as well for free for several dozens of pictures without payment. So kind of a nice web page, and you can also use different text, AI, and so on for marketing, content creation. And this was an interesting page of Explorer, which listed various tools on AI, which I definitely recommend you to take a look at to improve your work efficiency and other aspects. So let's take a look at this very brief demo of Dream Studio AI and what can you do with it. And this is how the Dream Studio looks like. It will generate you several pictures. Let's have 3 so it fits in. So after you register, you see a page like this. You can specify the size of your picture or to ratios. Let's do a portrait like this. And this is the prompt that you ask the model to build an image based upon, and you can even choose style. So let's choose style of a cinematic style, and I've got some prepared prompts there. So let's take a look at the prompt at the cat in gangsta style clothes with sunglasses, thinking about how to earn money in a busy nightclub. So yeah, and this is what the model generates. The pictures look really good, I think, and you can use them for your presentations or for being creative or something like that. So, and you can regenerate again and again. It will create you dozens of different images. Let's take a look at the second example of a medieval knight in a full shiny golden armor, sitting on a black horse, galloping through a plains with the lance pointed towards the enemy, preparing for a charge. And I wanted a photorealistic image. So some images are pretty nice. Sometimes the model may do weird things still, like the people will have 6 fingers, and yeah, there is a lance sticking out of nowhere, which is also weird. So you need to play with these prompts. You can regenerate it again, but we see that the results look pretty decent, even if there is no lance. For instance, we can try to generate once again. Maybe the results will be better. I don't know personally what the result will be. So yeah, it seems like there's a problem with the lance. There is a sword sticking out of nowhere. So the models can do interesting things, and it's definitely a nice thing to play with. Some models generate less nonsense, some generate a bit more. You need to play it, but most of them are paid because the training of the model and using them costs some money for the company. So they will charge you for it. Okay, let's conclude this presentation with the summary of what we've talked about and what may be interesting for you to take away from this presentation. So the key takeaways would be that the AI covers a wide range of systems that attempt to simulate an intelligent behavior to solve problems. And as we talked, in AI itself, the learning is not required because there are algorithms which do not require learning. Yeah, they use provided data. Then there is machine learning and deep learning, which are subsets of AI, and these actually learn from data. So these require learning and these learn. And the machine learning and deep learning versus regular algorithms or regular programming. In regular algorithms, we need to provide an exact steps as an input. So how to create the algorithm. And on the other hand, in machine learning, we only provide the data input and or input outputs, and the algorithm will get created by itself. So a different type of paradigm. We discussed three classes of machine learning tasks, which are supervised, unsupervised, and reinforced. Each is useful for specific use cases. We cannot tell that this is better than this one. No, they are used in different scenarios, different data availabilities, different algorithms, and as we can see in the modern large language models and chatbots, they can be combined together to create one very robust machine learning system. So we also know other like semi-supervised learning algorithms and so on, but they are typically variations of these three. Okay, there were a huge boom of deep learning and generative AI recently, which caused us to work with or to hear about the ChatGPT and heard about the language models. So this boom was changed by data availability, and was introduced by various other aspects, such as the new research progress and the match as the technology matures a bit. We've seen interesting things so far, and we will definitely see interesting AI things in the future as well. As we talked, the current AI is probabilistic and it doesn't understand the semantics of the text. So it understands the syntax, definitely, and very well, the large language models, but the semantics, it's still math, it's still probability, despite some researchers could argue that the models need to understand something because they wouldn't be able to generate such a quality text, and there is no like super conclusive answer to this, but I believe, and like many other people believe, that the AI cannot think yet and still doesn't understand the semantics. It's just some math, some statistics, and it's generating as the data. Yeah. And as we briefly outline, AI is here to stay and will impact many industries and jobs. Probably the AI and the generative models is a bit overhyped again, and maybe another winter of AI will come again, as we've seen before, but the AI will definitely not go away. It will keep with us, and it will augment our jobs and is already impacted and impacting several areas of our lives even more than we imagine. So thank you very much for your attention. I believe the presentation was informatically rich and useful for you. And I would like to close up with the quote from Stephen Hawking, who said that success in creating AI would be the biggest event in human history. Unfortunately, it might be also the last unless we learn how to avoid the risks. Thank you.